So next up, we have Stephen Wilson. Stephen comes to us from Arizona State University, where he was in chemical engineering. His advisor there was Christopher Muhich, thank you. And Stephen did a practicum at Pacific Northwest National Laboratory. Stephen, the floor is yours.
All right. Good afternoon, everyone. Thank you for the kind introduction, John. Currently I'm a postdoc at Arizona State University. I actually finished my dissertation last May, so it's been about a year now. But I'm going to highlight a bunch of different research that I did during my PhD. And then I have one slide at the end of something that I wanted to show off that's come out of my postdoc, actually. That I'll preface is what the CSGF really allowed me to work towards during my postdoc. So wasn't research done in my fellowship, but definitely highly contributed to, so I'm really excited. So as I discussed, it's a lot of different information or papers that I sort of condensed into one 15-minute slide. As John introduced, I'm a chemical engineer, but at heart, or by training, but at heart I'm a computational chemist, hence the computation part. And the computational chemistry can look at a bunch of different things. It's sort of the way it sounds is you look at chemistry, chemical reactions via computational means. And you can look at different interactions of configurations inside chemical systems. You can look at reaction pathways for different chemical reactions. And then you can look at different external effects at an atomistic level for these different systems. And so there's a huge breadth of information you can gather from computational chemistry. And I was really excited to hear from the incoming fellows, a lot of quantum chemists out there. So I think a lot more than I've seen in the past couple of fellow groups. So the chemical system that I'm going to be talking about for all of these slides is what's called chemical looping, where you take some metal oxide or ceramic material and you do a chemical reaction that can be cyclic. So you can do it over and over and over again. And there's different parts depending on the chemical reaction that you're looking at, where you can get your products either on this reduction side or products on the oxidation side. It really just depends on the chemical reaction. But the important part is that it's cyclic. So you can do it over and over and over again and regenerate that material. There's a lot of different chemical processes that rely on chemical looping. I won't go into detail on each, but if you're familiar, like CO2 capture relies on chemical looping. Some technologies rely on chemical looping air separation, energy in the form of chemical looping combustion, and then gasification. There's a bunch of different chemical processes that rely on this specific reaction. And so the current way you identify materials, how you compare and contrast materials for these different reactions, doesn't matter which type you're talking about, is there's a human interaction for the synthesis part, then there's a human interaction for the sampling and preparation to gather the data, and then there's a human interaction for the generating the model. And so that's the experimental side, and then it's the same thing on the computational, where instead of synthesis, you have to by computer generate your geometries and stuff like that. So my overarching goal, and it's a very broad thing, because again I'm tying a lot of works together, but how do we speed up this material identification and optimization of these materials for specific chemical reactions? I'm going to start first with just talking about how my work sped up the modeling side of the data that you get from your different chemical measurements. What I use is something called the compound energy formalism. It's a way you can decompose your material and gather the Gibbs free energies so you can access reaction enthalpies and entropies from that material. It takes the material and splits it into different sublattices, and it's the composition on those sublattices that define that free energy, where it's split into 3 different components here that each add complexity to the model. Now I'm going to break a cardinal rule, and I'm going to show a lot of nasty equations on a slide. But it's the important part here is why I want to show these nasty equations is that there's so many summations that you can see in these equations, and this is where the high performance computing part comes in. Because this compound energy formalism brings in all these different parameters in each of these different parts, save the entropy part, which is purely analytical, it becomes a very high degree of freedom problem. We're talking over hundreds of parameters that you need to optimize to determine, to fit this model to the data. And this is why the compound energy formalism really hasn't been used widely before my work in this field. So in order to answer that or compete with that high degree of freedom problem, what I've done is I've married the experimental data set with the computational data set. So the computational piece being that computational chemistry where my work was in gathering a large sum of data and taking that DFT data, marrying it to the experimental data, and then using both data sets to fit the compound energy formalism. When you marry those two, you get, that's what gets around your high degree of freedom problem, because now they share the parameter space. But you then have a new problem where you have sort of this Pareto front for those parameters, meaning there's a competing effect here. So I developed this workflow, and I won't go into it in detail, but it's a unique logic that gets around this high degree of freedom problem to get at these thermodynamic blocks, which is unique to this thermodynamic field because you gather a lot more information than the current methodology for extracting these thermodynamics. And so this is just a summary. You can take experimental DFT data set and pass it through and get these thermodynamic blocks in a high throughput fashion. So now there's no intermediate person needing to develop a very specific type of model to your very specific system. This works for all of these different chemical looping systems. All you need is the data and you get the result. So that takes off the modeling part. Now I want to look at how do we speed up this human reaction of gathering data. So how can we more quickly gather data to inform this model, and where the key trade-off is you want to gather as little data as possible but get the most robust model out of it. One thing I didn't talk about from the compound energy formalism is through my methodology you actually get several different models from the same data set. And so then you can use something called Bayesian inference to discern which model is the appropriate model, but you also get to play another trick where you can inform what data you should select based on those models. And again, some nasty math, but the important part is that we can use Bayesian inference and take this likelihood ratio test. From the log likelihood, you get this nice Bayes ratio where you can pick the appropriate model from the data and then pick the next data set, the next data point that you should sample just from your current information. The way this works is you'll take that Bayes ratio and start with some iteration of data. So your very initial data set, let's say, you have to start from somewhere, right? And then you pass it through your model, and then that'll give you a Bayes ratio value based off your previous model. So you start somewhere, gather your data, build your model, then do it again, and you iterate forward and forward until you sort of collapse at a converging set where the Bayes ratio doesn't change from one iteration to the next, which means that your data no longer improves the model that you've generated. And now you know that you've reached that most robust model with the least amount of data. And there's some literature on which values you can select as your cutoff criteria. So that's one hyperparameter in this set that you would have to select. But the important part, what it gets you, as I wanted to highlight, is that this black line is the ground truth. So in this data set, there were 100 data points, which created that black line. And at iteration 32, which was less than half of the data, so 44 data points, I created that blue line, which is the same thermodynamic trend with less than half the data. And so the way this works in theory, is you start with your very sparse data set. You pass it through that CrossFit CEF method that I introduced before this. You get your models, and then from those models, it tells you what point you should sample next. You add that to your data set, and you fit again. Now, that's one point at a time that I did sort of for this proof of concept, but in theory, what it would look like is something like this, where you span a very, very fine set of points. And then from those points, you get these hot regions of where the models disagree and where you should sample next to make your models collapse on those regions. And then that's what you'll sample several points from each of these regions and converge much more faster to your optimal model. And so in summary, again, we go through and just, again, now in a high throughput fashion. So now you don't have a person needing to decide and reprogram these different experimental data sets, which one comes next. You can link it to the previous high throughput workflow with the CEF, and now all you have to do is pick your material, collect your initial data set, and then let the high throughput process tell you what data point you should select next, and you just sort of follow the computer, and you can take yourself away from the mundane process of selecting and just focus on the science and what that data is informing you of. And so then that covers the high throughput data collection, and as you may think, I'll be moving on to that point, but I did not get to that side of things as far as the synthesis of materials since I was a computational chemist, but there's a lot of great work going on. If you've ever been to Berkeley's A lab, there's a lot of robotics going on as far as trying to increase the workflow or high throughput process for these syntheses. But what I will talk about is how I'm working towards expediting this data procurement for computational chemistry side of things. And so this is where I was talking about my postdoc work comes in. So I ended my dissertation with those two bulk methodologies. There's a lot of other work out of that. But all the stuff I learned in the DOE CSGF and all the extra classes I had to take and stuff really build a strong background that I can look into machine learning and AI for computational chemistry, specifically expediting computational chemistry. And then from that, me and my PI actually formed a company called SciForge that we're going to start producing these wrappers for expediting computational chemistry calculations. What we're looking at right here is a ground truth from a charge density of a chlorobenzene molecule, for an example. This is the prediction using SciForge, and if you squint really, really hard, which I don't think you can actually see on this screen, there's a little bit of purple in there for the error. So it's actually very, very small error. For clarification, we have this one-to-one line of the predicted on the y-axis versus the real on the x-axis, and that black line is a perfect prediction for the one-to-one. And so that's a charge density, and there's a lot of information you gain from the charge density. It's just some mathematics to get forces out of that, and then you can move atoms around from just this prediction. And so this will, we're still working on some time tests. I'm sure there might be a question about how much is the improvement. We are still working on that. But as you can see, with very low error, you can get really low error calculations for geometry movements through these computational chemistry sets, calculations. And so with that, I'm a little fast here, but I wanted to acknowledge my group at ASU, my PI, Dr. Chris Muick, the Muick Lab, of course, DOE CSGF, which all of my research was completely my own, and that was because of the CSGF, so thank you so much for that. And then all the computational resources along the way that I used throughout my project. With that, I will take any questions. Thank you.